So this is our last lecture today and for this event, and this is most appropriate that we are finishing it with a Irish lady representing physics, astronomy, astrophysics, everything that is exciting. Jocelyn Bell Burnell doesn't need introduction, I think, in this country and in this audience. But let me say several things about Jocelyn. The life story is amazing. Probably you have read online many things about Jocelyn. Just amazing. It's a dream for everybody to have this kind of academic story. Also affiliated to Trinity College, as she was for many years the Vice Chancellor. Pro-Chancellor, I'm sorry. Vice and pro, I always make mistakes. It's a shame. I am working at Trinity for 25 years. I can, Vice Chancellor, Pro-Chancellor.
Pro-Chancellor's less work.
Vice Chancellor is English, different post. I know, it's a different post. Pro-Chancellor. And when I was thinking what I have to emphasize from the achievements of Jocelyn in physics and astronomy and sciences. We liked, when I was young, to say the word science instead of particular science. I decided that somehow in my life, one of the big medals that Jocelyn had, which is Copley Medal, is distinguished. Every English friend I have tells me there is nothing better than Copley Medal. That list includes Faraday, Stokes. There are Irishman Stokes, who is from Sligo. There is Hamilton, of course, and McCullough, and so on. That, they say, in the British culture, is the highest achievement. Now, there are British people in this room. Correct me if of course, the many other medals, all deserved, and I think that we will see later today that she is national pride for Ireland. Okay, so please.
Thank you very much. Thank you. So this is an interesting arrangement, isn't it? It's clearly made for bigger people, so that's fine by me. I don't like hiding behind things. So thank you for the opportunity to be here. Thank you all for your staying power. We've had an interesting but quite lengthy conference already, so I appreciate your still being here. I'm going to say a little bit about my background. Then I'm going to tell you a story from radio astronomy about how these pulsars were discovered. One of the privileges of having discovered pulsars is every so often somebody comes up to me and says, "You know, I nearly discovered pulsars," and tells the story. And actually those stories are worth listening to because they also tell us a bit about how science really works. And finally, if I haven't run out of time, I'll try and identify the factors that I think led to the discovery. But I'm going to start with my background. And my background was in Northern Ireland, small town in County Armagh. And I started by failing what in England is called the 11+, what in Northern Ireland is called the qualifying. It's an exam that every kid sits at age 11+, because they believe at that stage they can distinguish between those who are going to have an academic career and those who are going to have a more hands-on technical type career. And your education post-11 is determined by the outcome of that exam. And I failed it. So I should have gone on to do cookery and needlework. My parents, however, were keen that I did science, and they also planned that all of us kids would go away from Northern Ireland for some of our education to boarding schools in England, because they felt the ambience in Northern Ireland was a bit toxic. Maybe it was a bit more than a bit toxic. So I went away to boarding school at age 13 and went through the English system, dropping just to 3 subjects in the final 2 years of school, which were maths, further maths, and physics. So you know where we are in Dublin. This shows various places where I studied. I started in Northern Ireland, then I get sent away to number 2, boarding school in England. I had identified astronomy or astrophysics as a subject I wanted to do at university, and for that reason initially chose Glasgow, then looked carefully at the syllabus. The whole of the first year was positional astronomy, and I thought, I want to do astrophysics. So actually I ended up doing a physics degree, which they called natural philosophy in that place, but it was straight physics, a 4-year physics degree. So I've been in the northern half of the country, and I've decided I want to do a PhD in radio astronomy. 2 places in Britain that do it, Jodrell Bank, which is near Manchester, and University of Cambridge. I'd worked at Jodrell Bank one summer as an undergraduate and been told by other grad students that they wouldn't take a woman. There's a dormitory on site at Jodrell Bank, and one of the young men and one of the very few young women had put the dormitory to a use for which it wasn't intended. He bragged. Sir Bernard Lovell, head of the Jodrell Bank, got to hear of it and said, "No more women." Interesting which sex bears the brunt of these mutual encounters, isn't it? So I didn't think I'd get into Cambridge, into Jodrell Bank, and I didn't think I'd get into Cambridge because I wasn't bright enough. I reckoned I was going to Australia to do this PhD in radio astronomy. But because there's a 6-month delay before the Australian year begins, I put an application into Cambridge anyway, and very much to my surprise, end up there. So I go from Glasgow to Cambridge. A bit of a contrast, folks. Cambridge was full of young men, very few women at that stage. I know that Boris Johnson went to Oxford, but they all sounded a bit like Boris Johnson. Walking the streets, talking in loud voices about what Plato had said and what Plato had not said, and blah, 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 blah. And I thought, oh my God, they're all very bright here. I'm not clever enough. They have made a mistake admitting me. They're going to discover their mistake and they're going to throw me out. Now, if any of the folks here are grad students or become grad students and you feel that, here's what you do. You say, okay, maybe they are going to throw me out, but until they throw me out, I'm going to work my very hardest. And that was my policy in Cambridge. And I was working really very, very hard, probably far too hard. But at least I survived. Yes, you can see this yourself. There is a gradient in the UK. Ireland, I think, is a bit more homogeneous, but maybe there's an east-west gradient in Ireland. And I've been in all these heathen places and suddenly find myself in this frightfully well-educated place. And I'm absolutely convinced they've made a mistake admitting me, and they are going to discover their mistake and throw me out. Discomfort increases when, within the first week, each of the new grad students is handed a set of tools. These are my tools. Still have them. They were the first tools I owned. These are not microelectronics tools. These are full-size pliers, etc., wire cutters, screwdrivers, and so on. Because I was going to spend most of the first 2 years of my PhD helping build a radio telescope. This is part of that process. It's winter time in Cambridge. Gets a bit chilly in winter in Cambridge. And my job has been to put, at this particular point, plugs and sockets on low-loss coax cable. You cannot coil low-loss coax cables up. You bust the cable if you do. You need to keep them straight. And so I've been working in this little red and white hut, and another one that you can see in the distance at the far end of the cables, putting the plugs and sockets on. And now I and the technician working with me are checking that the connections are good. We're building a very, very big radio telescope. It had over 2,000 antennae, 16 rows, over 1,000 wooden posts, 120 miles of wire and cable, an area of 57 tennis courts. Apologies, that's not a standard measure of area, but you can perhaps visualize it rather better. 57 tennis courts. It was relatively cheap because they didn't have to pay for much labor, £12,000, and it took 6 of us 2 years to build it. And this is the finished radio telescope. It's working at quite low frequencies. The wavelength is 3.7 meters, so the antennae are long. And what you can best see in this photograph are actually the wooden posts. The antennae are bare copper wires. If wet grass touches bare copper wires, signal runs to earth. So you have to keep the wires, the antennae, well above the grass. So you need lots of wooden posts. For those who want slightly more technical information, it was operating as an interferometer, electrically in 2 halves, and we could phase it. In this, you can see several rows repeating. If you put delays in between the rows, as it stands at the moment, the main way it's pointing is that direction. But if you put electrical delays in between the rows, you can swing the beam down or up. This is in declination for the astronomers. So, a lot of manual labor building that telescope. Because we had 16 rows, we could have operated with 16 beams if we could have afforded 16 receivers. We couldn't, we only had 4 receivers, so we operated with 4 beams set on different declinations. And we rely on the rotation of the Earth, so our 4 beams effectively scan out 4 strips of sky. And then Jocelyn goes out to the observatory and alters the angles of the beams, and they span another the next day, and so on. Transistors were just coming in, but they were really rather noisy and unreliable. So we used what we call valves, what Americans called vacuum tubes. And we had 4 of these, and that was 4 limited the number of beams. So that's the sort of technicalities of the radio telescope. Data came out on paper chart. University of Cambridge had 1 computer for the whole university. It had less memory than your laptop, and it took up a whole room because they didn't have transistors. They're using what we call valves, vacuum tubes. And you fed it paper tape or maybe a stack of paper cards. And one of the most important items were mothballs, because we programmed the thing to run for 24 hours. The moths like to settle by the reader, the light reading the punch paper tape or the punch cards. And so you had to get mothballs to keep them away from your punch paper tape that was commanding the telescope where to point. Right, so the purpose behind this thing. There'd already been a bit of radio astronomy, and the radio astronomers had identified some really very strong radio-emitting objects in the sky. And we turn to our optical counterparts and say, what is there at that position? Because it's belting out a lot of radio waves. And the optical astronomers would look at these things and say, well, they look a bit like stars, but we don't recognize the spectrum. And so they became known as quasi-stellar, or these days, quasars. Today we know that quasars are very distant objects with massive black holes accreting material fast. Back then, we just didn't know. But optical astronomers were turning their hands to help, and a couple of these objects had optical spectra. And in the States, Martin Schmidt had one of the optical spectra, and in the same department, further along the corridor, Jesse Greenstein had another optical spectrum. and they could not make sense of the optical spectrum. It seemed to be full of tellurium. Tellurium's not a very common element in the Earth and presumably not in the universe, so it wasn't making sense. And then Martin Schmidt suddenly had a rather ghastly thought, as he puts it. He says, it looks like a hydrogen spectrum, but with an enormous redshift. Could it be? He goes along to Jesse's office and says, Jesse, could it be hydrogen with an enormous redshift? And Jesse, oh, yes. The snag about the enormous redshift is that it implies it's at enormous distance, way beyond our galaxy, maybe 1 million times the distance of things in our galaxy. And yet it's strong. It's a strong radio source. What the heck is it? These things became known as quasi-stellar radio sources because they looked like stars with funny spectra, abbreviated to quasars. And I'm sure most people in the audience here today know that quasars are very distant, but they're galactic-sized objects with massive black holes accreting material very rapidly. So it finally became clear that these new objects discovered by the radio astronomers were extremely distant and extremely strong, which made them really quite interesting. But we only knew of a few, so my particular project was to find a lot more. And a little bit of physics here. If you don't like physics, just switch off for a minute or two. So up here, right up at the top, way off the top of the screen, there's a quasar. And the signal comes down through the solar wind, which is drawn as a series of blobs, down to the radio telescope on the Earth. The solar wind is highly ionized plasma blowing out from the sun all the time. It is not perfectly smooth. Some of it has got denser clumps, which I've represented as clouds. And these denser clumps behave a bit like a diffraction grating for the physicists. But it's a diffraction grating that's moving because it's blowing out from the sun all the time. So if you can imagine viewing something through a diffraction grating that's moving, you see it bright, you don't see it, you see it bright, you don't see it, you see it bright, you don't see it. And the kind of signal you get picking up down here is the kind of thing you expect when you're viewing through a diffraction grating. And this scale is about 1 second, so it's fairly rapid fluctuations, which means you can't use long integration times, which means you've got signal-to-noise issues, which means you need a ginormous radio telescope, like 4 acres, 57 tennis courts. Broad objects will not show that pattern, extended, angularly extended, but compact ones like quasars will, so it's a very, very neat way of picking out quasars. And it worked fantastically. When I started the project, there were about 20 quasars known. By the time I'd finished, there were about 200 because of this project. At that time, the University of Cambridge had a computer, one computer. It had less memory than your laptop. It was made with what the Brits call valves, the Americans called vacuum tubes. You know, things this sort of size with glass bulbs and very temperamental. So no way were we going to get time on that. Our data came out on very long lengths of paper chart, and it was my job to analyze these paper charts and make sure that the pen recorders had fresh paper in them and ink and all that kind of thing. We ran with 4 pen recorders. The telescope had 16 rows, so we could have run with 16 different beams if we could have afforded 16 receivers and 16 pen recorders. We only had 4, but that was plenty. As it was, I was getting 30 meters of that paper every day for analysis, and I observed for 6 months, so I ended up with over 5 kilometers of that paper. And I can tell you I have scanned every centimeter of those 5 kilometers, and some of it several times over. So what's going on, just to recap, is we're repeatedly mapping the sky to identify these new quasars. We're capitalizing on the fact that they're compact and they'll show this twinkling, this scintillation. We're using a short integration time in order to pick up the twinkling, the scintillation. And I observed for 6 months, and it was a very successful project. I got the number of known quasars up by a factor of 10, so that was fine. Having spent 2 years building it, my final year, because in Britain the funding is just for 3 years, my final year I was operating the telescope, analysing the data and writing a thesis, and incidentally discovering pulsars, so it was quite busy. Now this is a crucial piece of the chart recording. Maybe I'll go back. No, I don't have another chart recording to show you. Okay. So the main output from the radio telescope sort of drooled up and down, quasi-sinusoidal, as sources and things went past. But what we're looking for is very compact sources that will show this twinkling as the solar wind, as a diffraction grating blows past. So I'm not terribly interested in the slow drooly stuff. I'm interested in finding objects that go zzzz. And this line here shows some radio interference. If you have a radio telescope the area of 57 tennis courts, you pick up quite a lot of radio interference. And for a while, a pirate radio station found our empty band and used it and lost several weeks observing until they got shut down. But anyway, this is high-pass filtered. We've taken out the slow drooly stuff because I'm interested in the rapid fluctuations. There's a little bit of radio interference here, and here is the, actually with hindsight, first observation of the first pulsar. And they look different. Let me unpack a bit what I'm saying when I say they look different. In this one, the spikes go up and down. And you can sometimes see space between the spikes. They're lower frequency, and they've got positive and negative amplitudes. On this one, there are places where the spikes are so closely packed you can't see any chart between them. And the spikes go mainly up. There's a bit of an overshoot down, but it mostly goes up. So they look different in terms of frequency, space between the spikes, space not between the spikes, and in terms of amplitude, spikes go up and down. That, folks, is Fourier analysis in your head. You're commenting on the frequencies present and the amplitudes present. Or put differently, they look different. I knew that this was radio interference. We've got this ginormous radio telescope, 57 tennis courts. It picks up all kinds of interference, badly suppressed cars, not to mention pirate radio stations and other illegal things like that. So I'm fairly used to interference. This thing, I can't classify. And the first few times I log it with a question mark. And then your brain says one day, you've seen something like this before, haven't you? You've seen it before on this declination strip and from this bit of the sky, haven't you? And then it's easy. Having analyzed all these charts, I roll them up again and I store them in shoeboxes, labeled with the declination strip. And I was fortunate in that I worked in an attic. In the radio astronomy group, the grad students were in the attic. 6 or 8 of us along under the sloping roof, and down the middle was a great gangway that was clear. And it was a fantastic space for spreading out charts. So you could spread out several days' observations, line them up so that all the right ascensions are properly lined up. And once I suspected I'd seen that signal somewhere before, I started getting out previous observations of that declination strip and laid them out. So here's the one I've just seen. Didn't see it time before. Might have been there the time before that. That one I noted with a question mark, yeah. And I noted that one. And look, they're all at the same right ascension, and these are all the same declination strips. They're coming from the same bit of sky. It's probably the same source. So I go to my thesis advisor and say, Tony, what do you think this is? And he basically says, you bloody fool. It's all jammed into a 1/4 inch. We can't see what's going on. We need an enlargement. Well, with chart technology, enlargement's easy. You just run the paper faster underneath the pen, and it all gets spread out. But I can't leave the chart running at that speed all the time, or it'll get through a whole chart in 20 minutes. And guess who lives at the observatory putting a fresh roll of paper in every 20 minutes? Next best idea, grad student goes out to the observatory shortly before we're going to see this bit of sky, switches over to a high-speed recording, lets it run to about here, and then reverts to the normal recording. And I did that for several days, and I made high-speed recordings of receiver noise. And Tony, my thesis advisor, was not amused. It's been and gone and done it, and you've missed it. If there are grad students here, it's always the grad student's fault. You may have discovered that already. So it was my fault that it wasn't showing. But I persisted, and a day or two later, this is the high-speed recording I got. The bottom line is 1 second time pips. The middle line is the signal that came in, and you can see it sort of bumbles along. There's the odd bump. There's 2 or 3 bumps there, a gap, then a whole string of bumps. That labeling came later. You know it came later because you don't call the first one number 1 until you've got more than one. And you can see that there are pulses. Sometimes they go missing, but even if they go missing, it comes back on phase. So it's a very weak source. Sometimes you see the pulses, sometimes you don't. And the pulses are separated by about 1 1/3 seconds. So Tony's working in Cambridge. I'm out at the observatory. I risk his wrath and phone him up and say, Tony, it's a string of pulses 1 1/3 seconds apart. Oh, well, that settles it. It's man-made interference. But I knew it wasn't, because as you know, you see different constellations in the night sky and the summer sky. The stars come round every 23 hours, 56 minutes, not 24 hours. This is coming back every 23 hours, 56 minutes. It's not Joe Bloggs driving home from work in a badly suppressed car because he's getting off work 4 minutes earlier every day, and this has now been going on for several weeks. It has to be something connected with the stars, or at least something up in the sky. Could it be a satellite doing something funny? Well, we did some arithmetic. We couldn't find a satellite with an orbit of 23 hours, 56 minutes. So we were rather forced to believe it was something beyond the Earth, probably beyond the solar system. So it couldn't be radio interference because it's keeping this sidereal day, the 23-hour, 56-minute day. We enlisted the help of a colleague and his grad student, Paul Scott and Robin Collins. Robin also had a telescope, radio telescope, that worked at the same frequency on the same site. He was actually doing lunar occultations of sources to try and improve their position. But he had a separate telescope, separate receiver. And I remember vividly that particular day, the way the telescopes were orientated. My telescope saw that bit of sky first, and the thing, whatever it was pulsing quite nicely. And then we went and stood by Robin's pen recorder, and nothing happened. So there was Robin and I and both our supervisors, Tony and Paul. And the 2 supervisors start walking down this long laboratory. What could it be that shows in your telescope? Could it be? No, that won't work, but I wonder if it... No, that won't work. Well, I'm padding along behind, and Robin has stayed by his pen recorder. And we get down this long laboratory, and suddenly there's a shriek from Robin, "Here it is!" We went charging back, and there it was. Robin had miscalculated by 5 minutes when his telescope would see it. If he'd miscalculated by 25 minutes, we'd have all gone home and the story would be different. But Robin's telescope, separate receiver, separate pen recorder, totally separate kit, is picking it up. It's not that Jocelyn has wired up her radio telescope some stupid way. It has to be beyond the telescopes. So Jocelyn, keep observing this thing, and I did. I was quite clear it was keeping its period very, very accurately. It was not getting tired, which meant it had large energy reserves, which meant it was large. But it's pulsing quite fast and with quite steep rise and fall times, so it's small. So it's big and it's small. Very clear. So we got more and more interested. A colleague, John Pilkington, borrowed 2 of my receivers. Remember, I'm working with 4 beams. So he took 2 of the receivers, tuned one up in frequency slightly, tuned one down in frequency slightly, and after many attempts managed to get the pulse, going bleep, 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 bleep in the 2 receivers. The delay between the bleeps will give you an estimate of distance if you can make a guess at how many electrons there are in space. And John did that after a lot of hassle, finally got it, and showed that these things were within our galaxy, but way beyond the solar system. They're out amongst the stars of the Milky Way. We still don't know what they are. I'm still running the main survey. I'm still doing the data analysis. And after a while, I find a second, and a third, and a fourth. The first 3 all had periods of 1-point-something seconds. The fourth one had a period of 0.25 seconds. Considerably faster, clearly going to constrain the theory of what these things were. I was also repeatedly observing them because Tony argued that if it is really little green men, they probably live on a planet that goes round their sun. And some of the time the planet will be coming towards us, the pulses will pile up, and some of the time the planet will be moving away from us and the pulses will be further separated. So Jocelyn, keep observing this. We're looking for a Doppler effect. We couldn't find a Doppler effect. By now, we've been chasing this first one for several months. We know its period's very accurate. I think we've now got it to 6 decimal places. We know there's no other radio source at that position. John's got an estimate of the distance, a couple of 100 light years. Wonder what we do next. Well, I'm keeping the routine thesis work going. And one day, just before Christmas, I'm busy analyzing another piece of chart paper for the quasars, and oh yeah, there's one. Which is that? Oh, it's another one. And so it meant a trip out to the observatory, always at the dead of night, when that particular source was transiting, switching to the high-speed recorder, and in coming the blip, 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 blip. So the first 3 all had periods of 1 and a bit seconds. The fourth one I found had a period of 0.25 seconds. So clearly extending the range and extending the physics. And we couldn't find a Doppler effect. So we now had 4 of these things. It is honestly unlikely to be little green men. The chances of there being 4 lots of little green men, all deciding independently to signal to planet Earth, which isn't, that remarkable from outside. And we're not seeing any sign of a Doppler effect as they move on their planet around their sun. We still don't really know what these are, but clearly of interest. Having found 4 of them, we then wrote up the first one and said we've got another 3 of these and they're in the next paper, kind of thing. And And Martin Ryle, who was head of the radio astronomy group, telephoned the editor of Nature and said, we've got something interesting coming your way. Hold the presses, basically. And Nature published it very, very quickly. And all hell got let loose. The press got hold of it. The press suspected little green men. So we had to spend quite a lot of time suppressing the little green men idea. Then the press discovered that the grad student involved was female, and the photographers had a day. Please, could you undo some buttons, dear? How many boyfriends do you have? Would you describe your hair as brunette or blonde? No other colors were allowed. What were my bust, waist, and hip measurements? Clearly of scientific importance. The sexism was shocking. They would talk to my thesis advisor about the objects, what we thought they were, how they'd been found, etc., etc. But I was the sex object. And I must say, Tony did nothing to alter that arrangement. So it was pretty grim for a bit. However, Tony gave a colloquium in Cambridge just before the paper on the first one appeared, and gave it a very titillating title, and every astronomer in Cambridge came. It was a fantastic occasion. It included Fred Hoyle, which is a name that some of you will know. And Tony went through his spiel about what we'd found, and then talked about what these things might be. And there were two possible models. It could have been something vibrating, or it could be something rotating. We now know rotating is the correct model. The crucial test is, how does the period change with time? Because a rotating object will slow and grind to a halt. A vibrating object, as it ages, the amplitude gets smaller, but it actually goes faster. It quivers and then stops. So getting a period derivative was really, really important to help distinguish between those two theories. And we were getting there with the period derivative as well. So Tony gives this colloquium in Cambridge and announces what we've found and said, you know, the paper's in Nature tomorrow, and we've got another 3, and that paper's coming along behind. And Tony gave his favorite model of an oscillating white dwarf star. White dwarf stars are much, much smaller than our sun. Comparable mass, but a good deal smaller. And maybe they vibrate, and maybe as they vibrate, they launch shocks into the atmosphere, their atmosphere, and maybe somehow those shocks turn into radio signals that we pick up. Don't know. We weren't in a position to see how the period derivative changed at that stage. So Tony was proposing his white dwarf model. In the audience was Fred Hoyle. Fred Hoyle would be a name that's probably known to a number of you. He wrote science fiction books, but he was an outstanding astrophysicist, a theoretical astrophysicist, and a pretty blunt Yorkshireman as well. He did a lot of very, very good work. And when Tony had finished speaking at this colloquium, Fred was the first to speak up. Now, Fred's favorite cosmological picture was what was called steady state. Okay, the galaxies are moving apart, but according to Fred, fresh material could gather and make new galaxies to fill the gaps, so to speak. The other picture was of an expanding universe, which implied a big bang billions of years ago. Fred didn't like big bangs, so that Fred didn't like the Big Bang model. The early radio astronomy data was suggesting the Big Bang model was correct. So Fred was up against the radio astronomers, and anything he could do to show that the radio astronomers were stupid imbeciles was of big help to him in his theory. So Tony's presented what we found, and Tony presents his idea of an oscillating white dwarf. And Fred is the first to speak afterwards in his Yorkshire accent. I don't think it's a white dwarf. I don't think it's an oscillating white dwarf. I think it's a rotating neutron star. He's heard nothing about this data until 45 minutes previously, and he hits the right explanation immediately. He was a very, very good astrophysicist. The announcement produced a certain amount of scientific, not all scientific, interest. A lot of newspapers came to interview us, asking, typically Tony and I together, asking what we'd found and how we'd concluded what we'd concluded. And they were followed by the photographers. Jocelyn, please, can you do some buttons, please, for the photographs? As far as the photographers were concerned, I was a sex object. What were my bust, waist, and hip measurements? Not what science am I doing? What body do I have? And Tony wasn't prepared to intervene at all, so we just let it happen. Now, how am I doing for time? Got a bit more time, I think. Is that okay? Yeah, right. One of the wonderful advantages of having discovered pulsars is every so often somebody comes up to me and says, I nearly discovered pulsars, and tells me the story. And these stories also, I think, reveal quite a bit about how science is done, how science works. So I'll repeat to you as best I can some of the stories that I know about how pulsars were nearly discovered. And the first one goes back a long, long way to 1957. We're talking here about 1968, 1969, so 10, 12 years previously. We are in the United States at the McDonald Observatory. McDonald Observatory had a very fine 82-inch telescope given it on condition that the observatory was open to the public one night per month. And it's that night. It's summertime, and there is a student called Elliot Moore who's there for the summer, working at the observatory, and he's helping with this public observing night. And the telescope is set on what we call the Crab Nebula. Some of you will know a certain amount about it. It's a patch of nebula with a star in the middle, and we know that it's the remains of a star that exploded in 1054 AD. Ancient Chinese records give us that information, and sufficient information to be able to say, yep, that's the thing the Chinese observed exploding in 1054 AD. And there's a great big debris of glowing gas, and there's a compact object in the middle of it, known as Minkowski's star. And the telescope is actually set on Minkowski's star. And various members of the public step up to the telescope and say, oh, gee, wonderful, whatever were the buzzwords in the USA in 1957. And a young woman steps up to the telescope and says, that star's flashing. We now know that it does flash at about 30 times per second. It's quite fast, but some women can see 30 hertz. The main power supply in Canada used to be at 30 hertz. And there were a number of young women who were driven crazy because everything's doing this at 30 hertz. Doesn't seem to be that men can see it often, but specifically young women can see it. And this is a young woman who stepped up to the telescope and said, that star's flashing. The night assistant explained about turbulence in the atmosphere and scintillation. She said, no, I know about that. I'm an airplane pilot. This is 1957. She says, I'm an airplane pilot. My job is to fly aircraft from the manufacturer to the customer. I fly at night. There's not a lot to do in the cockpit at night, so I'm looking at the stars. And I know about the twinkling of stars. This is different. That star is flashing. Elliot Moore, the summer student, took note of this conversation, but nobody followed up. We now know that that star in the middle of the Crab Nebula is a pulsar that goes at 30 hertz, 30 flashes per second, which is about the limit that people can see. Young women, if anybody, can see it. And Elliot Moore believed that she saw the crab pulsar flashing in 1957 in the optical, and nobody followed up. Well, to be fair, there probably wasn't an instrument to follow up, but nobody showed any interest in following up. The next story dates from the early 2000s, when a US man by the name of Charles Schisler got in touch with the Australians who were doing pulsar research. The Australians have maintained an online catalogue of the pulsars that have been detected, and he's just stumbled across this catalogue. He says that when he was much younger and doing military service, he was posted to Alaska, to the early warning system, looking for missiles coming in from Russia. When things were quiet, his supervisor allowed him to play around with the equipment. He played around with the equipment. He found a number of flashing things that his radar system could pick up. He had done an astronomy course at college. He knew a little bit about the coordinate system, right ascension, declination. He made his best stab at the right ascension and declination of each of these flashing sources, and totally illegally took away that bit of paper with him when he left the US service. He has now just discovered this online pulsar catalogue, and about 10 of his flashing things are in the catalogue. The Australians quizzed him really very hard to see if this was genuine, and decided he was genuine, and he even came along to some of the pulsar conferences and had a ball, which was great. So I think I've probably said most of this. Highly classified nature of the work made it impossible for me to publish, but at the time carefully made notes of their approximate location. And then he's discovered the pulsar catalogue with over 1,700 sources in it, and he's finding that several of his objects are in that catalogue. So he probably observed pulsars with the US early warning system, but of course could never have published and might have had trouble being believed. In retrospect, the story is pretty clear. The final example of things almost being discovered dates from October, November 1967, which is around about the time we were finding these things. And it involves Sue Simpkin, who you see pictured here. Sue was brought up in Canada. Sue was one of the young women who experienced the Canadian lights and everything flashing at 30 hertz. And she was one of the young women who could see the 30 hertz fluctuations. She said it nearly drove her mad. At this point, she's doing, I think it's ultraviolet work. Lo Vulture, an eminent Dutch astronomer, asks her when she's next observing to take a spectrum of that funny object in the middle of the Crab Nebula. She does. She says the spectrum's dull, but she could see flickering. The Crab pulsar goes at 30 times a second, 30 hertz. She's one of the young women who can see 30 hertz. She reported this to Lo Vulture, who said, no, you're seeing things. I mean, she thought there were probably waves going out from it at that period as well, but Lo wouldn't believe her, and Sue dropped the matter. But when pulsars were announced, Lo was man enough to apologize to her and say, yeah, you probably saw it. This would have been about the same time as I was discovering pulsars, so it wouldn't change the date of discovery very much. The final example, I am not going to name the people involved. They were acutely embarrassed by the story I'm about to tell you. There's a group of radio astronomers making a survey of the whole radio sky at 408 megahertz. It means they get some time on that telescope and some time on that telescope and some time on that radio telescope. And they've almost completed the full sky, but there are some gaps, inevitably, which they are endeavoring to fill up. They're using pretty large telescopes, and if I remember rightly, this particular story happened at Jodrell Bank in Britain, which is where there's a particularly large radio telescope. The technology is still pen recorders. And one of the pen recorders is a bit sticky. And one day, or early one morning, early hours of the morning, that pen recorder starts going whoop, 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 whoop. And the astronomer in charge is not amused at 3 o'clock in the morning and thinks that damn pen recorder, and did what we always did to pen recorders, thumped it. That usually unsticks the pen. And the pen stopped going whoop, 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 and went back to its normal kind of wobbly trace. He did not make any entry in the log book. If he had, he could have claimed prior discovery of a pulsar, because the pen was going whoop, 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 because they were observing 0329 plus 54. But no entry in the logbook, nobody's going to believe them. So, yeah. He said, good. He put his coat on, he went home to bed. And even following the discovery of pulsars, that group did not think to go back through their records and see if they'd found anything. It would have been quite a mammoth task, but yeah, they could have given it to a grad student. So, yeah, a missed opportunity. And I haven't named them because they were always acutely embarrassed at having missed this detection. So those are the stories I know about the discovery of these signals. I want to finish with a little bit for the theory side. There was a wonderful Italian astrophysicist called Franco Pacini who tackled some of the really rather difficult things. And when Franco was in his prime, one of the questions was, why is the Crab Nebula still shining? We knew from Chinese records that it's the remains of a star that exploded in 1054 AD. It should not be shining so brightly now, that nebula. It should have faded a lot. It's actually quite a strong radio source. And a number of people tried to explain this, and it was Franco who actually hit the right explanation. He imagined a star at that stage of an unknown kind called a neutron star, very compact star, usually the core of a star that's exploded in one of these dramatic supernovae, and the core has been compressed in the explosion. So he imagines one of these neutron stars. He says it has to have a very large magnetic field, and the magnetic field has to be inclined to the spin axis. So if the spin axis is vertical, and this is the magnetic field direction, the magnetic field cones around as the star spins. Franco says that will make magnetic dipole radiation at this frequency. If that magnetic dipole radiation cannot escape the nebula but is dumped in the nebula, it will keep the nebula shining. And he was very, very largely right. Just 1 or 2 minutes more, if that's okay, just to pull out what I think were the key factors in the discovery, when it happened, where it happened. First of all, we had our own telescope and our own receivers. We were not using common user equipment, shared equipment. We weren't using borrowed equipment. And I made it my job to really understand the behavior of the telescope and the receivers. I'm a graduate student, a research student. I have time, space to follow up anomalies. Indeed, it's part of being a research student. It's how you learn. I'm being extra diligent because, remember, I'm in this very distinguished place called Cambridge. I've never been in the south of England before. They're all terribly bright, and I'm not. And they're going to discover I'm not very bright and throw me out. So I'm really working very, very conscientiously. This was one of the first observations made with a short integration time, a short time constant. Radio astronomers up till then had no reason to use short integration times, and longer integration times would give you better signal to noise, so why not? But for my particular project, we needed the short time constant. And although it's perhaps not such good science to make this last point, we weren't aware of other observers likely to stumble over this data. So we didn't have to publish tomorrow. We could take time to check out that the signal really was genuine. And then when I found another 3, we became more confident. So that was good. We had a good address. If you're going to find something totally unexpected, verging on the outrageous, a good academic address is a great help. People are more inclined to believe you. But increasingly in Britain, particularly for research studentships, you're meant to declare the goals of the targets, the goals of the project, and afterwards you're assessed by how completely you've met those goals. This couldn't have been one of the goals. We didn't know these things existed. A computer might have marked us down for deviating from the goals. And you will have noticed that this was done at relatively low frequency radio astronomy. For many, many years afterwards, radio astronomers moved to higher frequencies, shorter wavelengths, better precision. There is now a drift back at last, but it's a domain that has been neglected. So thank you for your interest, thank you for your attention, thank you for the opportunity to be here.
Thank you very much. It's a fantastic story, and I think that many of us would say that would be good to be in this life like yours. It's very special, and we congratulate you again so many years after. Questions, please?
Well, first of all, thank you for a fascinating insight into this discovery, and really was beautifully presented. I've always wondered, as you know, the Crab Nebula was first observed by the Earl of Rosse with his Leviathan, which was basically a big light bucket for naked eye observing.
Yes.
So had a young Canadian woman looked through the Leviathan, would she have seen Minkowski's star pulsing and pushed the discovery back into the mid-19th century?
Probably. But it probably would have to have been a female who had that extra acuity for the high frequencies.
Exactly.
And would she have been believed? A woman? No.
But the Earl of Rosse, member of the Royal Society?
Yes.
Yeah.
Yeah.
Again, thank you very much. This was a beautiful recounting of all of these exciting discovery, and also the perspective of a woman in those times, which I was not aware of. I'm interested in neutron stars. This is what I work on. What did people know at that time about neutron stars? It's not that we know a lot nowadays, but what is it that people thought?
Yeah.
Do they know about the mass, the radii? What did people know?
I'm not absolutely sure of the answer to that question, but I suspect they knew mass radius. There was actually quite a conversation going on amongst theoreticians at that time that we were unaware of about what neutron stars might be like, or what highly magnetized stars might be like. So they would have probably not able to do any of the internal composition, which is quite interesting. But I think they would have had some idea of sort of overall mass and radius. And magnetic field because it's collapsed, yes, of course. Yeah. Well, it depends what you mean by no. Theoreticians made statements.
Thank you for the talk. It was incredible. I just wanted to ask, how long after the detection of the pulsars did the telescope that you were using stop being used?
There was another generation of graduate student took over after I used it, built it and used it. I think then it stood unused for a very long time until the price of copper went up, Rhodesian crisis. All the antennae, twin wire feeders, are copper wire. And one dark night, some people came in with wire cutters and removed all the copper. So no radio telescope anymore, nothing to collect the signal.
Thank you so much again. Let's thank Jocelyn for this great lecture.
Thank you. Thank you very much.
I have not been very consistent doing what I'm going to do now, but there is this, I forget, I remember, there is this coin of dedicated to Hamilton. 20 years ago, when we created this institute, the government agreed to make the coin. Now I want to give it to you for future memorabilia.
Very
As you
fine.
see, there was a fight about to have Nabla, age for Hamilton, but on the other side is a harp. You know, harp was never debated. So Nabla won, and it used to be available in our shop in the Book of Kells, you know, but not anymore, like for 10 years. But I happen to have this for distinguished guests, and so I forgot to give Gregory a previous lecture. But I squeezed in the coffee break, and yesterday I forgot for anybody, but all of them eventually I gave. So I'm sorry for those, but this is something that many years from now will be, I think, remembered. It was a special event. Second thing I want to say is that it is so amazing that we closed this important event that I wanted to plan for many years for many reasons, and somehow was not sure that it will work well. But you closing it was a perfect closing I could imagine. You know, we started with Hamilton, great Irishman, and we finished with great Irish woman. This is how world is changing.